So, as we've seen in the presentation before, we heard a lot about the toolchain. And now there's one big part missing, and this is the FlexTiles simulation environment, which is based on open virtual platforms. And I will start this presentation with explaining a little bit what is OVP, what makes it special, what are the advantages, and in the next point, why do we need it, why do we want it in FlexTiles. Then I will continue with a small recap. What is the hardware platform we want to model in our simulation? And what do we need to do to achieve this? And then finally, I will end with the actual strong points of OVP. I go a little bit into detail into this and showcase this in two small demos. But first of all, a reminder, where are we again in the toolchain? So if you think back at the top, we have the whole high level, the whole development environment, which is the front end of the whole toolchain. Then we have the separation in the left part with the hardware part, and in the right part, which is the software part. And then down on the bottom, we have the actual back end, which is the prototype, the emulator, and which is the OVP platform. And one thing we can already notice here, the application bundle that is created, it's intended to run on both, on the emulator and on the OVP simulation. This is one of the big goals we had to make it consistent, to make it the same for both flows. So, what is OVP? Basically, it is a higher level simulation. And as with all simulation, the goal is to have it early available and to be able to debug something, to develop something early and without the availability of the actual product, of the actual hardware. And so in OVP does this on a very high level of abstraction. And this is a general trend, this what could be observed in the past. So starting, a good example is System C, for example. In the beginning, System C was very similar to those hardware description languages. So it was designed to be similar to VHDL, Verilog, and so on. And then people started to think, yeah, we need to get it faster. And so there were publications, there were efforts, and it was quite successful. It was going faster, but still not very fast. And so at some point, it really was clear we need to go to high abstraction levels. We can't go on with this full accurate models if you really want fast simulations. And so this is what was done with System C by introducing the TLM, the transaction level modeling. And this only defines interfaces between components, and then the components could be modeled on a very abstract level and getting a lot faster. And this is where now OVP comes into play, because OVP is basically the extension of all these efforts. It is a completely new framework, yet it is still designed for good interaction with System C. And it is based, what makes it so fast, so it is based on binary translation. And what is binary translation? So the applications are compiled into the target architecture code. So the models we have in OVP, they take these instructions, these applications, and take each instruction and translate it into a native instruction of the host processor, where the simulation environment is executed on. And this is what makes it so fast. And the other big advantages are the platform access API. So you could really observe everything what's happening in the platform, every register, everything. And it has GDB support to extend on this. Furthermore, we can easily extend all the platforms by creating our own models. We could even create our own processor models, but especially we're interested in peripherals which can do all other tasks that are not directly the processor. So this is OVP, and why do we need it? So as I already mentioned, it's tailored to fast execution speed. This is what's important in OVP. And this is actually what we need, because in the FlexTiles project, one of the big focus was on the development of the software and the tool chain. And we have a very complex software part with operating system, with management services, with resource managers and everything. And so it was really important to have this stable, to be able to develop on this, to get started before the hardware is fully integrated. And even then, even when the hardware is fully integrated, we still have advantages with OVP, because especially compared to the embedded system that's targeted and to an emulator, OVP is still fast and can still be faster. And we will see this later. And this is a big advantage. And of course, recompilation of the platform, you don't need any of the synthesis flow. It's just a matter of seconds in OVP. Yes, and so that's what's important for us, and not that it's cycle accurate. So, because we don't need this feature, OVP is the right choice for us. But now let's get back to the actual platform. What do we need to model? So if you look here, so first in yellow on the top we have several GPPs. Now there are 3, but there could be any number in OVP or in the platform. Then next part, the whole blue part in the middle, this is the network. But for OVP, we don't really need to know, oh, there's a network interface, oh, there's a network and chip, oh, there are routers and everything. We just need to know how can we interconnect the GPPs, how can we interconnect the tiles, how can we interconnect the accelerators and everything. So here's a big possibility for us to bring in abstraction to make the models fast, but to be completely compatible to the software and the operating system, so no changes are needed. And yeah, what else do we see? We see the AI, so the accelerator interface, which hides again the accelerators. So again, for us the important part is how does the interface to the accelerator work, and not how do the accelerators work. We just need to model their functionality, not how they're exactly executed. So to bring it together, we need the GPPs, but OVP already offers a model for the microplace. We only had to do a slight adaptation because one instruction was not supported. We need UART timers. There are already models available as well. They're not exactly compatible, so there needed to be small adaptations again, but it wasn't a big deal. And then the next three devices I will go into a little bit more detail, which is the monitoring core, mostly used for debug output, which is the interconnection device, and which is the accelerator interface. So first off, the monitoring core. Exactly like on the real platform, the monitoring core is there to push out the debug information. And for this, it's connected to each tile via an FSL link, which the microplace offers. And so each of these compose tiles can send the debug information to the monitoring core, and it gets printed out via the UART. In our case, it gets printed out into a file on the host system. And it uses exactly the same operation, exactly the same FSL operations. In the OVP platform, we use the monitoring core for the shared memory and the video input-output as well. So they could be on a separated instance as well. This is just an optimization. So next up is the interconnection. So here we have the whole stack. 2 tiles, at the top the tasks, at the middle the operating system, and then at the bottom the hardware part. And at the left and the right each 1 tile. And so what do we need for the interconnect? The tasks, they don't want to know anything about the interconnect. For them, the model of computation is a CSDF. So they just know, okay, I need data so I can start processing, and I need to push out some data. Okay, fine. And then the operating system. The operating system knows about, what are the addresses, what are the targets of each task, and how do I get there. But still, the operating system on the hardware level, it just knows DMA transfers. It just tells the DMA, okay, take the source, take this address, this size, this many bytes you have to transfer, and then it goes through the network interfaces, the NOC, and everything. In OVP, really, the only important part is to model this DMA, which is able to connect to the other tiles. And so we did exactly this, and it's fully compatible with the driver code on the operating system, so the operating system won't notice that there's no hardware below it, but in fact it's just this device in OVP which does all the interconnect. So next up is the accelerator interface. Here we see the actual accelerator interface with all the channels and everything. And you see, yeah, this can get quite complex again. But for us in OVP, we can keep it simple. We just need to comply to the driver code, so it gets accessed exactly the same as on the platform. So we implemented the AI as in a special environment that's exactly useful for this, for developing peripherals. And in this environment, the code gets actually executed on the host. So this achieves that we are actually faster when bringing software from the simulated processor, so from the microblades into the accelerators, which is a nice benefit. And we can actually model delays. So how long does it take for a calculation for an accelerator to finish one chunk of work? And basically, what we can do with the accelerator interface is to model those high-level synthesis tools, because we can take any C code, not just a subset, and insert it into one function, which then is executed natively on the host and is our accelerator. So those are the three, or basically now we have built our platform. And now we get on to the interesting stuff, which is really nice about OVP, because as I mentioned before, we have the GNU debugger fully working on the OVP. We can use it to debug all the application and software running. We get error messages by the simulator. Anytime something strange happens, addresses are accessed that are not allowed. So it's really good visibility, and you can observe everything, not so much like in the hardware. And even more, we have the full accessibility, which allows us to build our own tools and our own methods to enhance the abilities by GNU, and so by GNU debugger. And so I will show right now a little tool we have prepared. So the first one is a stack tracing tool, which lists the stack usage and the calls, so which functions are called. And we will execute this on a dry stone, which is a processor benchmark. It's not so important. The interesting part is that it has 1,000 iterations. So, and we will see this soon. So, and it's actually quite fast. Yeah, it's just a small code. We can use the stack trace, of course, with huge applications as well. However, yeah, you need to specify how much you want to log, because otherwise it can get very big. So, and what do we see here? So we basically see every call that is done in the program, and it's ordered by a number of calls with no stack usage. And so, so at the top first, we see the actual stack usage in bytes. There we have 2,320. And so we can use this tool to execute any application. We don't even need the source code. We just take the application, run it on a platform. On the platform, this whole stack tracing is activated, and then we get such call graph. And where we see here at the bottom, we have this proc 3 and 1. Those are the main computing functions in this drystone, and they are called exactly 1,000 times because it has 1,000 iterations. And then on the right we see the average stack usage for each call and a summated version of this. So this can actually help us debug programs or, for example, port it to an embedded software where our space is actually limited. While in the OVP, yeah, we have almost limitless space. So this is one of the nice things, and yeah, we can extend this. We can create complete call graphs and everything. And yeah, because we have this full visibility of the platform. And next off, another very nice part about OVP is then we can make a connection with the host system. And this allows us to use resources of the host system, for example, to actually connect sensors or to actually connect video in and out. And this, how we do this. Well, there are two graphics to show this. So first of all, in gray, we have the host system. So in our case, in this example, this is the laptop here. On this laptop and the host system, the OVP environment is running, which is seen in blue. And we see there we have the CPU, memory, and the PSE. PSE is a peripheral simulation engine. So this is how we model our additional devices, our peripherals. And it's still within the simulated environment. But we can access the host as well via a semi-host. This allows us to map, for example, in this graphic at the top, native host memory into our simulations. And this we can use to access files, for example, but also, for example, video in or video out, because yeah, they are file-based devices as well. And for this we have another demonstration. You've seen the SUSE application before. It was described in the presentation before. And basically we use exactly the same setup. We use exactly the same application. And now we're executing it in OVP on the microplace and see what happens. Yes. So, as we can see here, we actually use the camera from this laptop to get the video stream in, and then we have the SUSE application running on this video stream. And yeah, it's not perfectly fluent, but it's quite fast. So especially if you compare it to how long it took to build one image before, this is quite fast. And you see the SUSE edge detection been done on the fly. Yes. So to come to a conclusion with this, OVP allows us really fast simulations. Yes, currently OVP is still sequential, so with bigger multi-core platforms with a lot of load on each core, it would perform not as good compared to the emulation, but it's still quite a bit ahead right now. So yeah, this would still be fast, and especially parallelization of OVP is a matter which is possible, and we already have some prototypes of it working. So yeah, there's a lot of room to improve as well. We have a complete model, a complete simulation model of the hardware platform, of the FlexTiles platform, and it's working. And it's working completely compatible with the operating system and the whole software. And the strong selling points we have now are the debugging capabilities. So for porting new applications to the system, for helping in developing the operating system and the resource models and everything. And we were not limited by the hardware. For example, we could easily say, oh, now we have another sensor here on this tile or on this core, which is not present on an emulator board, or which would be very costly to implement again. And we have, more or less endless memory, for example.